Here we have another example of designing a counter. We want to design a counter using D-type flip-flops and gates to repeat the sequence of states 1 to 6. So that's what we want to have. Yeah, we want to have repeating of the values 1 to 6. So we start from scratch. We can form the state table. We can start to form the state table. We would need to have 3 bits, A, B, C, for the current state, and for the next state we will have DA, DB, and DC, or A at t plus 1, B at t plus 1, and C at t plus 1. We'll start from 0, 0, 1, and the next state will be 0, 1, 0. Then 0, 1, 0 will take us to 1, 1, 0, and 1, 1, 0 will take us to 0, 0, 1. All the remaining possible combinations for A, B, and C could be considered as don't care. So don't care for 0, 0, 0, 0, 1, 1, 0, and it 1, 0, 0, 1, 0, 1, and 1, 1, 1. All these cases will be considered as don't care. Now we can form Carnot maps to find out the expressions for DA, DB, and DC. Here we have A, B, C. Let's fill it. We have only for 0, 0, 1 for DA. So for this part, 0, 0, 1 will give us 0, 0, 0, 1 will give us 0, 0, 1, 0. This is indeed 1, 0. 0, 1, 0 will give us 1, and 1, 1, 0, 1, 1, 0 will give us 0. And the rest are don't cares. Just make this clear. Here we have 1, 0. Okay, then we can easily find the expression for DA. We can combine this 1 with any of its adjacent minterms. I can pick this one, so this will give me DA will be equal to not A and B. So not A and B will be the expression for my DA. I can do the same thing for finding the expression for DB. For DB we have 0, 0, 1 resulting in 1. So 0, 0, 0, 1 will give us 1. 0, 1, 0 will give us 1. And 1, 1, 0, 1, 1, 0 will give us 0. And the rest again are don't cares. Now the simplest expression for DB could be obtained as not A. And finally for DC we can obtain it. For DC we have, let me just complete this, 0, 1, 0, 0, and 1, 0. For DC we have, for 0, 0, 1 we have 0, for 0, 1, 0 we have 0, and then for 1, 1, 0 we have 1, and the remaining minterms are don't cares. And now you can see that the simplest expression for DC could be in the form of A. Now we can start to draw the schematic for our counter. We are going to use D-type flip-flops. They all receive the clock pulse directly from the system. So this will give us QA, QB, and QC. For A, we have not A and B, so we need to have one AND gate. Like this, not A and B. For B, we have not A, so I can directly connect it to the negated output of the first flip-flop. And for C, we have D equal to A. And I think I can do it in this way. We can also introduce the reset, the asynchronous reset to our counter. And one more thing here is that we can also determine what happens when we happen to be in one of these don't care states. Yeah? When we are in 0, 0, 0, for example, we can find out the values for DA, DB, and DC. Let me just fill it according to what we have found here. So DA is not AB, not AB will be equal to 0. DB is not A, so we'll have 1 here and then 0 here. Then for the next state, 0, 1, 1, we have not AB equal to 1, not A will be 1, and A will be 0. So similarly, we will have A here, and not A for B, and we have not A and B, which will result in 0, 0, 0. And now we can also complete our state diagram. If we happen to be at 0, 0, 0, so from 0, we will go to 0, 1, 0, which is 2. So from here, we will move here. If we are in 3, we will go to 1, 1, 0, which is 6. If we are in 4, we will go to 1. So from 4, we will move to 1. And from 5 and 7, we will also go to 1. So you can see that in one clock pulse, we will transit to one of the main states of our counter if we happen to be in any of the don't care cases.